In the previous video, we have a baseball player, and he's throwing a fastball, and he wants to get the greatest change in momentum possible out of his swing. So how does he do that? Well, in order to get the change in momentum to increase, he increases the force that he applies to the ball, and he increases the length of time that his bat is in contact with the ball. But now we're moving on to a second case, in which momentum is decreasing, and the goal now is not to maximize the change in momentum, but to minimize the amount of force that's acting on the object in question. In this case, the change in momentum is fixed. It's always the same. It's not getting smaller or larger. And so in order to minimize the force, you can increase the length of the interaction. If you want the force to get even smaller, make the length of the interaction even longer. Now, why would we want to do this? Stop running in the hallway. I'm going to write every single one of you a report.
Poor brother Matt. He sustained a lot of force in that collision. How can we diminish the force from that collision? Maybe if we increase the time of it, so the net momentum change will be the same, so from full speed to stop, but we'll increase the time that takes by making an airbag. Stop. Perfect.
Running in the hallway. How many? I'm going to write every single rule.
Case 2 is behind the science of airbags. The basic idea here is that you're going to crash no matter what. You've already got a lot of momentum, and something's about to happen to kill all of that momentum. And it's going to take some force to make all of your momentum disappear. Momentum just doesn't go away like that. And in order to improve your chances of survival, you want to make that force as small as possible. It turns out that the best way to minimize the forces involved is to maximize the amount of time it takes to decrease your momentum. Let's walk through this. If you have a fast-moving car hitting a haystack or a cement wall, it's obviously going to have some very different results. Now the question is, number one, the car hitting the haystack, does it have the same change in momentum as the car hitting the cement wall? Question number two, does the car hitting the haystack have the same impulse applied to it as the car hitting the cement wall? Question number three, do both experience the same force? Pause the video now to determine your answers. You can choose A, yes for all three, B, yes for 1 and 2, C, no for all three, or D, no for 1 and 2. And the correct answer was B, yes for 1 and 2. They are going to experience the same change in momentum. Alright, we're assuming both of these cars have the same mass, so that doesn't change. And both of the cars are moving at the same speed when they hit the haystack and they hit the wall. So they're both going to experience the same change in momentum. They both end up at a speed of 0. So same change in speed, same mass, same change in momentum. Secondly, the same impulse is applied to both cars because impulse equals momentum. So if the change in momentum is the same, then the impulse has to be the same. But there is a big difference in terms of the force. The car that hits the haystack is going to experience a much smaller force. Sorry about my face being in the way there. Be sure to distinguish, important, among momentum, impulse, and force. When a dish falls, will the change in momentum be less if it lands on a carpet than it lands on a hard floor? Think carefully now. Think about the example with eggs, the egg lab we did in class. A, are they both the same? B, is it yes, less if it lands on the carpet? C, no, less if it lands on a hard floor? D, no, more if it lands on a hard floor? Pause the video and determine your answer. The change in momentum for both is the same. Same idea as before. The momentum is becoming 0 in both cases. It's changing by the same amount, therefore. But though it changes and the impulse is the same, the force is less when you extend the time of the momentum change. Common sense tells us that it would be better to hit a haystack than a brick wall when you're in a collision, but physics tells us why. A fixed change in momentum requires a fixed impulse, but the longer the time interval of the impulse, the smaller the forces involved, right? Small force, long time interval, fixed change in momentum. Same change in momentum here, but in this case the time interval is tiny, so the force has to be huge. This is why you bend your knees when you jump, or you ride with a punch. The change in momentum and impulse in each case, it's the same, but you're minimizing the force by extending the time that it has to change your momentum.
Two eggs, same mass, drop them from the same height and they'll hit the ground with the same speed. Because their mass is the same, they'll undergo the same change in momentum. It'll go from a positive number all the way down to 0. How do you prevent the egg from breaking? To minimize the force on the egg, maximize the amount of time it takes for the momentum to go to 0. Ready? Ta-da!
Can't really see the egg.
Science.
What's your challenge, Matt?
Challenge is as follows. Could we do this same experiment, but from the top of a building, or say off of the track into the gym? How would you construct a mechanism to protect an egg from breaking? You need to construct something that would maximize the amount of time it took for the egg's momentum to go from the positive number down to 0. It's a challenge for you.